Hello, Mr. Wilson here, coming at you with 3-7 graphing all polynomials. So go ahead and take out your homework packet and we're going to turn to page 34 and we're going to complete problems 1 through 4, obviously excluding number 2. As we go through this video lesson, every time I'm going to want you guys to pause or stop the video, this little button's going to pop up, and go ahead and just click pause and let the students do work or have a discussion or whatever. Okay, so appreciate that, and let's continue. So question number 1, it says create or sketch the graph based upon this given information. And I believe we have enough information here to do like a rough estimate. Okay, it's not going to be completely off. So let's see what we can do. It says that it's a cubic function. Okay, so that means that we've got something to the third power. That's the highest degree. And then it has 1, -0. So when it comes to the coordinate plane, we know one of the zeros, one of the x-intercepts, is going to be on this side. I don't know where, but it's going to be somewhere over here. Now, since it says multiplicity 2, multiplicity means that when we were doing this polynomial and we got it to factored form, whatever was the negative, remember taking the opposite of this would create a -0, whatever the negative 0 or factor was had a multiplicity. Okay, multiplicity of 2 means that it was squared somehow. Okay, and then since it has one positive, that means the other one that was positive, I don't know. I don't know if it's 2, but it could be somewhere over here. Okay, so now whenever we have multiplicity of an even number right here, 2, 4, 6, whatever you want to do, okay, that means that the graph, the function, is going to have what's like a bounce off the x-axis, almost like bouncing a ball off the ground. Okay, but in this case it's going to be a little bit different. Since we're dealing with a cubic function, we know that it's going to have a disco type like end behavior. So we know that this is going to come from this direction as we're going to the left, and then it's going to be coming like this as we're going to the right. Okay, so what the multiplicity tells me at this 0 on the negative side, that means that it's going to be coming up here and it's going to bounce off, come down somewhere, and then go back up. I don't really know where this is. This isn't that important right now. You'll learn that later. But roughly, this is what that function would look like. Not too bad, right? So we are going to skip this one, but I wanted to just show you this. Whenever it's talking about a double root is kind of like this multiplicity, this plus or minus type deal that we got going on. Okay, anyways, number 3, a cubic function with with 0 real roots. Zero. That means that they don't have any real roots. So think back when we were dealing with like a quadratic, a parabola. If I was to put this on the coordinate plane, we know that it would cross right here and then go up. Okay? So if I added something to this, like if it was like +2, that means that this graph would shift up 2 units. And so if it shifts up 2 units, where is it crossing the x-axis? See, it doesn't have any real zeros. It doesn't have any real solutions, real x-intercepts, but it does. I mean, you could kind of solve it. Okay, and I'm going to get into that a little bit more later. So if a cubic function doesn't have any real roots, meaning like it never crosses the x-axis, then what the heck? How could that possibly happen? If it's cubic, we know that it's a disco, and so that the end behavior is going in opposite directions. So how does that translate? How does it go from here up to this and not cross the x-axis? Well, obviously it's going to have to cross the x-axis, and so when it does, it's just that it's not going to have like any factors that look sort of like this. So it's just going to cross right through the origin, and basically that's all we could really do with that. Okay, the next one right here where it says a quartic function, that just means that we're dealing with something that is raised to the 4th power, like that. Okay, so it says 0 real roots, and then it has a positive leading coefficient. So positive leading coefficient means that it's going to be opening upwards, okay? And then it says it has a positive y-intercept. So if we're looking at this as it's crossing the x-axis, well, hold on. Is it going to cross the x-axis? No, it's not going to cross the x-axis, but it has a positive y-intercept, and that's all I really know. So it could come down, do a little bendy thing, I don't know, and then go back up. Okay, so that's what that one would look like. Good deal? All right. So I'm going to show you the answers to the problems that we did last time. And you could pause this if you need. Here's this page. And if you have any questions, just let me know next time I see you. Okie dokie. Alright, let's get started. Alright, so here's 3.7, graphing all polys. Our objectives today is we're going to understand complex numbers. And when we say complex numbers, we're talking about these things right here, imaginary numbers. Okay, so I equals the square root of -1. I'll go into that in a second. And then last, we're going to be creating polynomials from the zeros. All right, here we go. So where does I come? Where does an imaginary come from? I don't get it. Why do we have these things called imaginary numbers? Well, it all comes back to a square root. Okay, something happens whenever we take the square root. Okay, the square root, this little guy, all right, even as innocent as this looks, this is asking a question. It's saying to all of us, hey, what number was squared to get 81, right? So whenever we take the square root of 81, we think to ourselves, oh, well, 9 was squared to get 81. Okay? So this is how you might want to look at it. What number was squared to get 81? Well, that's the 9, right? So if we have something that is a negative, let's say we have the square root of -81, all right, it's asking that question, what was squared to get -81? And obviously we could look at this and be like, well, hold on a second. Whenever I square a number, whether it be positive or negative, it's always going to end up being positive. And so now we have like this thing where we're like, hold on a second. There's no real number that exists that can make this true. Unless it was an imaginary number, like an imaginary 9, right? So that's what we would say. The square root of -81 would be 9i. Okay, so see if you guys could do this. What's the square root of -25? Good, 5i. Pretty simple, right? Okay, so whenever you're dealing with a square root that has a negative, I want you guys to think about it like, let's say that we have the square root of -9, okay? We could look at this as breaking this into the square root of -1 times 9. This is the same thing as this, right? And so whenever you have a negative, just take that out as an I. So we have I times the square root of 9, and the square root of 9 is 3. So this would be 3i. I know I just complicated the crap out of that, but just bear with me. It'll make sense when I give you something like this. Okay, you're looking at this right now, and you're like, oh, wait a second. What do I do? Well, first, just take care of the negative. Okay, pull that sucker out as an I, and now you can kind of deal with this. The square root of 24 isn't a perfect square, but we know that a perfect square is one of its factors. So the square root of 4 is going to be 2, and we can't take the square root of 6. Okay, now remember that I that was hanging out all alone by itself? It's still out there. Okay, and so what we're going to do is just kind of sneak them in right there, because this is all being multiplied on the outside. Okay, got it? Awesome. Let's keep going here. So let's see if you guys can pick up on this pattern. If I had the square root of 3 times the square root of 3, well, that would be the square root of 3 times 3, which is the square root of 9, which is 3. You follow me? So then if I had the square root of 5 times the square root of 5, going through this whole thing, I would just get 5. So if I had the square root of 7 times the square root of 7, I'd go, well, that would just be 7. So if I had the square root of 9 times the square root of 9, are you following me there? Then that's just going to be 9. So if I had the square root of pi times the square root of pi, I would just get pi. So if I had the square root of -1 times the square root of -1, what would that be? Did you say -1? I wasn't there. I couldn't hear. So if you guys said -1, good job. Okay, because hopefully you saw that this pattern was going, and I wasn't trying to trick you. I just wanted to see if you guys could get this. Okay, so this is what this tells me. This tells me that I know I equals, well, I, right? And, off to the side we could say that's the square root of -1. But if I had I squared, I squared would look like this, right? I squared times, right? So then that means that that is negative 1. Okay? And now if I was to do I to the third power, well, that would be the same as multiplying these two things, because that's I squared times I. So negative 1 times I, that would be negative I. And then if I had I to the fourth power, that would be the same as taking I squared times itself. So if I had negative 1 times negative 1, that would be positive 1. So this is what I want you guys to do. Next time you're going to take a test, you're going to write down I, and then you're going to write down I squared, and you're going to write down I cubed, and you're going to write down I to the fourth, and you're going to do this little thing right here. Ready? You're going to say, I won, and then put the negatives in the middle. I won, negatives in the middle. Got that? And so anyways, whenever we're dealing with an imaginary, like a variable, the I, and then it's raised to a certain power, this sequence just repeats. So this is I to the first, second, third, fourth, and then up here it goes 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, right? So each of these, it's always going to be 1 on every fourth exponent. So see if you guys could take a second and figure out what I to the 13th would be. So how I usually do this, if you're stuck, is I look at this and say, okay, well, I know 12 is a fact, right? 12 and 4 kind of go hand in hand. So 12 would be right here, so 13 would then be right there. Does that make sense? All right, so anywho, good luck with that. So let's try simplifying some of these radicals. So this right here, how do we simplify this? How do we simplify this? This. So I know normally we would say, hey, we can't do this because we've got a negative underneath the radical, but I want you to give it a shot. Take a few minutes, work with the people around you, and see if you guys could get these simplified. All right, so the first one's real basic. You just have the square root of negative 1 times the square root of 2. Square root of negative 1 is I, and then you have radical 2. Now over here, the square root of 12, negative 12, you have the square root of negative 1 times the square root of, well, 4 times the square root of 3, right? Square root of 4 is 2. The square root of 3 we can't take, but then the square root of negative 1 is I. So we put the I right there. Okay, that's how you simplify this. Now over here we have the square root of negative 1 times the square root of 36. So that's going to be 6, and then that's going to be I. So that's how we write those. How do we do up there? All right, now here it says write this in the form of a complex number where it's a plus bi. So I see that this is going to be the real part, the 7. Okay, so I'm going to put that first, and then the bi right here, this I have to simplify the square root of 18. So 18 is the same as 9 times 2, right? And then I have times negative 1 to get that. So the square root of negative 1 is I. The square root of 9 is going to be 3, and I can't take the square root of 2, so it's just going to stay like so. So now I'm going to add this to this. So I've got plus 3i radical 2. That's how you complete that one. Okay? Alright, moving on. How about right here? These ones are a little bit more tricky. Okay, and the reason why is because a lot of you guys don't realize, oh no, these aren't the tricky ones. These ones are easy. All you're going to do is just combine like terms. Okay, we could do those ones. You could do them on your own. Okay, down here, these are the tricky ones. These are tricky because you have to multiply I times I. Now, I times I is going to give you I squared, which is negative 1. So, take a second, try number 5. Alright, so over here, we have 12 times 7, which is going to give us 84. Then we have I times I, which is I squared. I squared equals negative 1. So we have 84 times negative 1, which would give us negative 84. Okay? Over on this side, we have to use FOIL. So 6 times 4, that's 24. 6 times negative 3i is going to be negative 18i. And then you have this middle term right here, the two inner terms, that's going to be negative 20i. And then you have these last terms, which is going to be a positive 15i squared. Combine the like terms, so we have 24, negative 18i negative 20i. So these two guys, these are, you can combine these. So that's going to be, what is that going to be? Negative 38i. Okay. And then lastly, we've got something crazy right here. Notice that this is 15 times I squared, which is negative 1, right? The I squared is negative 1, so that's going to be a negative 15. Alright, so I color coordinated the ones that are like terms. Obviously, these are like terms. This one is not because it has the I. So 24 minus 15, I think that gives me 9. So 9 minus 38i. Okay, that's how you do that. Same deal with this one. So use the distributive property, and then in the end, we get 43 minus 24i. Let's move on. Alright, so what this slide is saying is basically this. Let me sum it up. If you have radical negative 2, okay, times the square root of negative 3, does it equal this? Negative 2 times negative 3. Right? So is this true? That's basically what that slide was just saying. So that's the big question. So why don't you guys talk real quick, see if this will equal the same thing. Alright, well first off, if I have radical 2 times radical 3, you could just multiply. So this is the same as 2 times 3, which is the square root of 6. Okay, so it's legal to do that as long as it's multiplication. If it was addition, you couldn't do that. So let's try this. Over here, negative 2 times negative 3, that's going to just be positive 6, right? So will this equal positive 6? Well, before we multiply, we have to take care of this negative, right, on the inside. So this is the square root of negative 1 times the square root of 2, right? So that one's going to be I radical 2. And then this one in the same story, right, is negative 1 times the square root of 3, which will be I radical 3. Now we just multiply these two things, and so you've got I squared, and then radical 2 times radical 3, I did it over here, is just going to be radical 6. Now what is the I squared going to give us? A negative. So we have the square root of 6 on this side, and then we have negative square root of 6 on that side. So obviously these ones are not equal. So just watch out for that. Whenever you have a negative, just you gotta branch it out like this and pull out the I before you start to do any other operation. Okay? Alright, so let's try to solve this. So since this is an equation, all we're going to do is just get the variable by itself. So the first step is I need to get rid of this 54. Subtract 54 from both sides. Right? Then I'm looking at this. To get rid of the 9, I divide both sides by 9. And then I have x squared equals negative 6. How do you undo a square? Well, you have to take the square root. So whenever I take the square root of a variable, I have to put plus or minus, and then I have a negative 6. Now before, right, I've been training you guys that this is bad, okay? And that's only bad whenever we're talking about domain, because we can't have imaginary numbers for the values of x. We can't plot that on a coordinate plane. However, we can simplify this and say that our answer is just going to be imaginary. And so this is what the imaginary number would look like. We pull out that negative 1 like this, and then we know that that's going to equal I. So then that would be your final answer. Okay? And everything's pretty much as simple as that. Okay? It just gets a little bit more, problems that you're used to. This is like an Algebra 1 problem. Alright, so why don't you guys pick one. Pick either A, B, or C, and try to solve those as a class. Okay, part A, I got plus or minus 4i. Part B, I got plus or minus I radical 30. And then C, I got plus or minus 1/2 I. So how'd you guys hold up there? Do all right? Good. Are you really responding to me as I ask you guys questions? Because that'd be kind of silly, right? Because I'm not really there. Okay, so another thing that we're going to be looking at today is long division of polynomials. Now I know that sounds just like a horrible thing, but it's really not that bad because you guys all know how to divide. Like if I was to say 20 divided by 5, you guys would all know that it would be 4, right? And the reason why this is 4 is because really when we're looking at 20, we're thinking that it's the same thing. Well, we're factoring this. 4 times 5 equals 20, right? And then if we're dividing it by 5, those two common factors divide out and we're left with 4. Okay, so what if we have something that 5 doesn't go into evenly, like say 22? How do I divide this? Well, we look at this and say, well, that's an improper fraction. I know that 5 goes into 22 at least 4 times, and then there'd be 2 left over, and we'd say, okay, then that would be 2/5, right? So the remainder really is this portion right here, the 2 over 5. So when we're looking at dividing polynomials, keep this in mind. And also, I want you guys to, let's say that we have 223 or something, and we're dividing this by 5. How do we do this process of long division? What's our first step? What do we do? Well, we look at this and say, okay, if this is 5 and I'm trying to divide it, I'm figuring out what's another factor that 5 times something would give me this. Okay, so 5 doesn't go into 2, 5 goes into 22 at least 4 times. And then what do we do from this stage? You put a 20 down here. Okay, where did we get this 20? Didn't we say 4 times 5? So 4 times 5 would give me 20. And then what do we do with these two numbers? Don't we then subtract, or basically take the opposite? And when we do that, we get the 2 from the 2 minus 0. And then the 3, we go ahead and bring this down like so. Right? We're not done yet, because then we'd have to say, okay, now how many times is 5 going to 23? Again, it's 4. And then we multiply that, and we get like this. And then we have 3. And 3 ends up being our remainder. So then we would say that this is 44 and 3/5. Does that make sense? Okay, so we're going to be using the same concept, the same procedure for basically dividing polynomials. Now I know, don't be scared. Look, you're okay. So this is the number portion. Okay, notice that this is called the divisor. This is the dividend, the thing on the top. This is our quotient, and then what we have here is our remainder. Okay, same thing is going to work here. This is our dividend. This is our divisor. Here's our quotient. That's our remainder. So how are we going to do this? It's kind of annoying. I'll be honest with you, but I know that you guys could do this. Okay, so here we go. How do I go from x to x squared? Okay, well, don't we multiply by x? And then so from here, to figure out what goes underneath, we're going to take this x and multiply it times this x to get x squared, and then take this and multiply it times that as well to get a negative 5x. Now we just don't simplify this, okay? We have to take the opposite of these terms that are down below here. So subtract the x squared, which also means that we're going to be, taking the opposite of this negative 5 and make it a positive 5, and we get something like this, okay? Now we could bring down the negative 30, but how do I make this x, into a 7x? Yeah, we would have to do a 7, right? So then from here, 7 times x would be 7x, and then 7 times the negative 5 would give us the negative 35. Don't forget to take the opposite. Okay? So then from here, that becomes a negative 7, and that becomes a positive 35. We have a remainder of 5. And so how we write this is we take this number and put it on top of what we were dividing it by. Okay? So that's using long division. I'm going to show you guys another method. It's called synthetic division. So check this out. Here's the example. So we have all of this stuff, and then it says divide this by x minus 3. So that's what it would look like if I was going to do long division. But instead of doing long division, there's a more like direct way called synthetic division. And first what you have to do is come up with the 0 for what you're dividing it by. Okay? So what is the 0 of x minus 3? Don't we just set these things equal to 0? Right? And so you'd have to add 3 to both sides, so we know x equals 3. Well, that right there, that's going to go inside this little magical box. And then I'm going to take these random numbers that you would have no idea where I got them from, right? And then from there, this is how synthetic division works. Okay, so first we're going to bring the first coefficient down. So the 5 gets like a free pass, goes straight down. Okay, then from there, I'm going to put a number here, but the number that I'm going to put there is going to be the product or multiplication, 3 times 5, okay? And then I put that right there as 15. And then I'm not adding or subtracting here, I'm just combining, okay? A positive 15 and a negative 6, that would give me 9. Okay, then I'm going to do the same procedure, 3 times 9, okay? That'll be 27. Just combine here, so I get 31. Multiply again, I get something like this, and then bam. Okay, now how this works is this last term, this is your remainder, okay? So that would be the thing that goes up top, okay? And then this is your constant, this is your x term, this is your x squared term, okay? So, kind of get it? That's synthetic division. Hey, what would happen if I got a remainder of 0? What would that mean? I mean, if we were to go back and look over here, whenever I get a remainder, that means that that number doesn't go into it. That means that it's not a factor. 5 is not a factor of 223. So if I do get a 0, then I'm kind of in business, right? That means that I just figured out another factor. Okay, right here. So the next thing that we're going to be looking at is it says find all the zeros, which is a synonym for solutions of this particular polynomial. So we've already done one like this. Before we use the x, we have to make it look like a quadratic. So we're going to factor out, right? Factor out the x, and then we're going to use the x to figure out what the solutions are. But what if the x doesn't work? What if I can't use the x, man? What if I can't, the x, there's no factors of 1 that would give me -1. So how am I supposed to find the solutions? Well, we've got 5 different ways that we can solve a quadratic, so let's just use that other one, right? We have the quadratic formula, okay? So quadratic formula for the second half, which is going to kind of suck, and when we do that for the quadratic formula, we get something like this. So we still have that x equals 0, that's up there, and then we also have that. So that would be the solution for that ugliness. Okay? Why don't you guys see if you can try to do this? Look, I know what you're thinking. Wait, Mr. Wilson, that one was a lot easier than this one. Yeah, well, of course it was. This one has 4 different terms. This one only had 3. So even if you pulled out something, like let's say if we were to factor by grouping, I don't think we're not going to even be able to factor by grouping because you're going to have a 7 and over here this is going to be a 1, okay, when you pull out an 18. So there's another method that we can use in order to figure out what the solutions are. So remember, factors are really important, okay? And one of the ways that we can find factors, like let's say if I have 63 and I want to know what a factor of 63 is. Well, I could just say, you know what, I want to divide this by 9. Okay, when I divide 63 by 9, I find out what the other factor was, right? So I know that 9 and 7, those are both factors. So how do we do this for this kind of a thing, right? Right here. How do I take a polynomial that has 4 terms and understand what's going on? Because look, do you guys see how on this side, it actually gives us one of the zeros. It says that this is a solution, okay? So we're going to use this technique that I don't know if your Algebra 2 teachers taught you, but it's called synthetic division. Okay, so we're going to take this factor, or this solution, and since this is a factor like this, where that's going to be x plus 3, okay, I already know that one of my factors is this. I'm going to divide this into here to see what another possible factor could be. So watch what I do. I have to keep the -3 whenever I'm using synthetic division here. Let's look at what that says. Okay, so synthetic division, I put the -3 on the outside, and then where did I get this 1, this 7, this 18, and that 18? Anybody know where I got those numbers from? Oh yeah, they're the coefficients, right, to this polynomial up here. So how we do synthetic division is like this. The first one always gets a free pass, okay? So the 1 comes down. Then the -3, you have to multiply the 1 times the -3. -3 times 1 is going to be -3. Then we just combine. So 7 minus 3 gives me 4. Now, what's the number that should go right here? Tell your partner. -3 times 4, that'll give me -12, right? Then we combine, we get 6. -3 times 6 gives us -18. So this is how it works. Watch this. Whenever you get a 0, that means that it goes in evenly. And we already knew that. And we knew that it was a factor, okay? And how I always remember this is, since this goes away, then that means that this is your constant, this is your x term, this is your x squared term. Okay, and then if you had more terms, then it would be like this, x cubed, and then x to the 4th, then x to the 5th. That's how synthetic division works. Okay, that's after your remainder is so this is always your remainder right here. Okay, so I know that one of my factors, looking over here, is x plus 3. Okay, so this one is 1, that one's 4, that one's the constant term, okay? And then I also have x plus 3. This is in factored form. Now to find out what the solutions are, well, we take the opposite of this one to get x minus 3, right? And then how do I find the solutions for here? Are there factors of 6 that would give me 4? Yeah, no, so then we're going to just have to use the quadratic formula. Okay?
So just trust me that when I use the quadratic formula, I end up with this ugly thing right here. Okay, those are the solutions. Notice that we have 3 solutions. Okay, so I have a solution here, and there's 2 solutions here. See, whenever there's a plus or minus, that means you have to add it, and then you have to subtract it. So I've got 3 possible solutions. Notice that I'm also looking at the degree to see how many possible solutions that I can have. Okay, up here, this one has a 3, and we have 1, 2, and 3 possible solutions. Okay? All right. What about this ugliness? So we have a degree of 4, and it looks like this, and then it tells us that we've got this solution and we've got this solution. Okay, so we're going to use this synthetic division like we did a while ago, and we're just gonna hash this thing out and see what we get. Okay, so first step, we've got the 2 factors already as x plus 1, x plus 1. Okay, I already know that. Okay. Now I'm going to use synthetic division. I'm going to put the -1 in the little box, and then I'm going to say 1, and then the -1. Wait, how come? Where did I get the 0 from? Turn to your partner real quick and say, hey man, how'd you get this 0 up there? Yeah, whenever we're doing synthetic division, if we're missing a term in the sequence, like we don't have a cube term. Since we don't have a cube term, we put a 0 placeholder in that position. Okay? So, remember the first one gets a free pass. Then the second one, we have to multiply this times this to get the -1. Then we have to simplify, that becomes -1. Why don't you guys see if you can finish up the rest of this synthetic division. Alright, so multiply negative times a negative, that gives me a +1. That's going to give me 0. This times 0 is going to be 0. Then bring down the 2. It gives me a negative. Okay, so this 0 right here, remember, that's my remainder. That's my constant. That's my x. That's my x squared. This is my x cubed. Okay, so x plus 1, we know that one is already there, right? And then now we have x cubed, x squared. We don't have an x term. My constant is 2. Got me? All right, so my solutions are -1, -1, but then how do I figure out what the solutions are of this? Well, since we still have a cube, we're not there yet. We have to try to strive to get this to look like a quadratic. So that just means that we need to divide it again using synthetic division. Remember how we have a -1 and we already have, okay. So we've still got an x plus 1, right? There's 2 of these. So let's still use synthetic division, but put -1 in here, and we're just going to do it for this portion of the factored form right here, okay? So that's the 1, that's the -1, there's a 0 placeholder, and that's the 2. So why don't you try doing synthetic division there? Alright, so the 1 gets the free pass. This times this gives me -1, that'll be -2. This times this will give me +2, 2, multiply, you get -2. Okay, so now that's a remainder, that's my constant, that's my x squared. Okay, so now I have a quadratic. And remember, we have an x plus 1, and we have another x plus 1 also. So this is what this thing looks like in factored form. So to find out what the solutions are, we take the opposite of this. That's going to be -1. Opposite of that is -1. Still the same thing. Now, are there factors of 2 that would give me -2? Nope. So what do you think we're going to have to use? Yep, quadratic formula. So if we do the quadratic formula for that, we're going to end up with something like this. Nice job. Just when you thought all the complexity was all done, there's one more thing that I really need to hit, and then we can take it from there. So here's the deal. If I were to say that the solutions were x equaled 2 and -3, you'd be able to tell me what the actual polynomial looks like, because you'd just go backwards. You'd say, well, if I got a solution of 2, that means that the factor looked like this, right? And then if I got a solution of -3, that means that the factor looked like this. And then all you'd have to do is just multiply. So that's x squared, that's +3x, that's -2x, and then that's -6. And then you could actually figure out what the polynomial look like if you have the solutions. Do you guys see that? So that's where we're going now. I'm going to show you the solutions, and then you're going to be able to figure out what the polynomial was. So, like, what happens if you have something that's complex, though? 2i. Okay? Like, if I told you that x equaled 2i, what the heck? Okay, well, how do we get imaginary numbers? We only get imaginary numbers whenever we take the square root. And then whenever we're solving and we take the square root, that means that there used to be something that was squared. So that means that there's going to be plus or minus. So whenever you have 2i as a solution, then negative 2i will also be a solution. Do you guys see how these two numbers, these are called conjugates? Okay? So if you know that 2i is a solution, or it tells you, then that also means that this is a solution. Now, how do I write that as a factor? Well, it's just going to be x minus 2i. That's what this one will look like. And then this one is going to be x plus 2i. Okay, so we would just distribute, and then we can figure out what what the polynomial would look like. So let's try this one, and then I think I'm done. All right, so first off, it says it's a degree of 3. So I know that it's going to be like x cubed, blah, 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 right? It says that the solutions, or the zeros, are x equals 2, and then the other one is going to be 3 minus I. Now, if 3 minus I, since this is complex, is a solution, I also know that 3 plus I is going to be a solution as well, right? Because these are both conjugates. All right, so the first one's going to be x minus 2. And then these two guys, I'm going to do these over on the side, okay? Because I'm going to multiply these first. I have 3, hold on. I have x minus, watch this, 3 minus I. And then I have times x plus 3 plus I. Okay, so look, this looks confusing. I'll simplify it in a minute. Don't complain and cry. Okay, so see, I'm taking this, and one's negative, and one's positive, right? So I'm taking the same deal. Okay. Oh, excuse me. Hold on. I have to take this. Has to be minus. Here, let me just erase it. And why don't I just erase half this thing? Okay, minus. All right. So I'm taking the opposite of these two things. So there's both minus sign right there. Now let's simplify. I have x, and then distribute. That's going to be minus 3, and then that's going to be plus I. That's what this first thing is. Then in here, this is going to be x minus 3, and then that's going to be minus I. So to simplify it, you're not going to like it, but just get over it. X times x is going to be x squared. X times negative 3 is negative 3x. X times negative I is going to be negative xi. That's the first one. Okay, now the second one, I'll do in a different color, the negative 3. Negative 3 times x will be negative 3x. Negative 3 times negative 3 will be positive 9. Okay, and then negative 3 times that will be positive 3i. Now the last one I'll do in orange. I times x is going to be positive xi. And then I times negative 3 will be negative 3i. And then I times negative I will be negative I squared. Okay, so a couple of these things are going to cancel out. Do you guys see that? So the negative xi and this positive, so that's going to cancel out with that. This is going to cancel out with this. The 3x, did I do that right? I think it should have canceled. That's a negative 3x, and then that's a negative, no, okay, so that worked out. All right, so I have x squared minus 6x, and then a 9, and that's going to be minus a negative 1, because I squared is negative 1, so that's going to be plus. That's going to be 10. All right, so then to add this to the party, I'm going to have x squared minus 6x plus 10, like so. Now I got to multiply this, so this is going to be pretty. All right, so x times each of these is just going to add another x. So I have x cubed minus 6x squared plus 10x. And then if I was to do the 2 times everything, that's going to be minus 2x squared, and then positive 12x, and then that'll be negative 20. So I'm just going to combine everything, and then I got my polynomial. So x cubed minus 8x squared plus 22x minus 20. Whew. There we go. Nice job. All right, so next we have this thing that's called the factor theorem, and it goes along with this other thing that's called the remainder theorem. Okay, so the remainder theorem basically states this before I get into the factor theorem. Let's say that we have a polynomial. We'll call it p of x, okay? And it's got a bunch of like ugly stuff. It's like 2x squared plus 7x. Let's make it to like the 12th, okay? And then, you know, whatever, 4 plus blah, 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 whatever, okay? Now, what this is saying then is if you were to take another like thing and try to divide it by it, let's say it's like x plus 3, okay? If you want to see if x plus 3, if you were to put that in there, okay? So if you have this x plus 3 and you want to know if this is a factor or are you going to get a remainder. So what you would then do is if you put in the 0 of this, which is negative 3, and then substitute it into all of the values. So you've got negative 3 to the 12th power, plus 7, and negative 3. Then whatever you end up getting, okay, whatever you end up getting on this side over here, this would end up being your remainder if you were to try using synthetic division with this, okay? So what the factor theorem is saying is that if you end up doing this and get a remainder of 0, then you know that this is a factor of basically this polynomial. So let me show you what I mean by that. Okay, I've got a short version there. That's basically what I just said. So let's take this example, number 4, and it tells you that this is a factor. Okay, it says that x plus 3 is a factor, but I just want to show you how this factor theorem works. If we were to put in the 0, what would be the 0 of x plus 3? Yeah, wouldn't it be x equals negative 3? Okay, so if we were to take this function and evaluate it at negative 3, it would look something like this. We have to take that x value and first cube it, and then we would have to take it and then square it, and then that's a square, and then we'd have to take it and multiply it times 4, and then we've got the 12. Okay, so watch what happens. We don't really, I mean, I know this looks intense, but it's really not that bad. Look, negative 4 and negative 3, isn't that going to give me a positive 12? And isn't that positive 12 going to cancel out with that? Okay, and then over here, negative 3 to the 3rd power would be negative 27. And then here, negative 3 squared, that would be 9. Times 3, that would be 27. So here, this is 27, a positive, and then we have a negative 27 right here. So see how this would cancel out? So if f of negative 3 equals 0, then I know that x plus 3 is a factor. Does that make sense? You guys get it? Okay, so that, again, is the remainder theorem / factor theorem. Okay, so that's kind of a useful tool, you know, because instead of using synthetic division, you could just substitute the whatever it is, and then if you get 0, then you know that you're dealing with a factor. Okie dokie? All right, so this is what you're going to see on your test if you guys are curious, okay? So let's just run through this real quick. We're not going to do it all, but could you tell me if these are the zeros or the roots, what would say the factors look like? What would this look like as a factor? Well, yeah, we'd have the x minus 3, and then this would be x plus 4, and then what would this be? Yeah, that would just be an x on the outside. Then we would distribute it all and then get that. Okay, now here we got some more imaginary. Let's just run through that again. What would just listen, we're just looking at factors, okay, so don't get scared. What would be the factors here? So you have x minus 5, and then here we have x minus 2i, and then we have x plus 2i. Is that making sense? Okay, and then here, whenever we have a radical, it's just like with the imaginary. We're always going to have its conjugate as well. Okay? So, good luck. I want you guys to work on, let's see what your stamp sheet says. Work on these pages here for 3-7, and I will see you next time.